All right, hello again. So I said I would never use that board over there, and I plan to stick to that, but today it's off camera. But I want to refer back to this axiomatic system that we were using last time quite often throughout this class today. So I've just thrown up our undefined terms from last time, fees, foes, and belongs to, and the four axioms that we had from last time. And I ended last class, well, we ended with a proof, right? We had proved that in this axiomatic system, we can prove, based on these axioms, we can prove other statements that are true. For example, we proved that there must be at least 3 foes. And I left you with an exercise saying, prove that there's actually exactly 3 foes, right? And the way you would do that is say, well, suppose there's more, suppose there's 4 foes. And you can show that that gives you a contradiction. By the way, I wanted to point out in the proof we did last time of proving there's at least 3 foes, if you read through the proof again, you'll notice we only use the first 3 axioms, right? So if I were to come up with an axiomatic system where I just erase this fourth axiom, that theorem would still be true in this sort of new axiomatic system. If you want to prove that there's exactly 3 foes, the proof of that would have to invoke this 4th axiom somehow. And I think I built a model using lines and points at the end of last class, and that's where I want to go today. We want to talk a lot about models. So what is a model? It's basically just a realization of our axiomatic system. So we can create an interpretation of an axiomatic system by giving undefined terms a particular meaning. All right, and if we do this, if the axioms are still true, correct statements, then we've established a model. So if the axioms are then true or correct statements. The textbook, I think, uses the term correct all the time here, which I understand why, but it reads a little bit nicer. I think if you just say true statements. If the axioms are then true or correct statements in this interpretation, we call it a model of the system, of the axiomatic system. So I suppose we can start off with the one I had last class, at the end of last class. So for example, let's go with a geometric model. Let's say our fees, these are going to be points. Fees are points. Foes, I will give this a real interpretation. Foes are lines. And belongs to how are we using belongs to in this axioms? Any 2 distinct fees, so any 2 distinct points, belong to exactly 1 foe. So let's say belongs to means is an endpoint of. So when I say a fee belongs to a foe, I'm saying a point is an endpoint of a line. All right, so there's our interpretation, and I'm just going to restate the axioms using this terminology, this language. So axiom 1 now becomes there's exactly 3 points. You've got exactly 3 points. 2 any two distinct points are endpoints of exactly one line. Three, not all points are endpoints of the same line. You might say that's a little bit redundant under this interpretation, right? Because I've already told you in axiom 1 there's exactly 3 points, and it's sort of impossible for 3 points to be the endpoints of the same line, right? Because every line has 2 endpoints maximum. And 4, any two distinct lines, let's phrase this as any two distinct lines share at least one endpoint. Any two distinct lines share at least one endpoint. Would you agree that using this terminology, that's what axiom 4 says? Is that an okay way to phrase that? Any two distinct points, any two distinct lines contain as endpoints one point that belongs to both. Yeah, this should be what this says, right? Just worded slightly differently. And I already gave you the model last time, so here's sort of a, what I need to do now is verify that these statements are true, right? They sort of don't contradict each other. So let's see, I have to have 3 points, so let's go 3 different points. 1, 2, 3. I need any two distinct points are endpoints of exactly one line. So if I choose any 2 points, say these 2, they have to be endpoints of a line. So between them, I have to have a line. Have to, if I'm going to make this true. I can have this pair as well. So these 2 distinct points, those have to be endpoints of a line. And we've got the bottom 2 points here. Those have to be endpoints of a line. Okay, now axioms 1 and 2 are true. Is 3 true? Not all points are endpoints of the same line. Is that the true statement in this drawing? Yeah, right. For example, this point is not an endpoint of this line. So not all points are endpoints of the same line. That's good. And last but not least, any 2 distinct lines share at least one endpoint. So if I choose any 2 lines, for example, these top 2 lines, do they share at least one endpoint? Yes, that guy. If I choose these 2 lines, do they share at least one endpoint? Yes, that guy. If I choose these 2 lines, do they share at least one endpoint? Yes, that guy. So all of these axioms under this model, all of these axioms are indeed true. Right, by the way, this is the model, right? This is the model. All I've done is rewritten the axioms over here to verify that they are true under this model. But that's the actual model, this sort of triangle. And yeah, so let's just make an observation that it's a model and all axioms are correct. Or true. Awesome. By the way, this model doesn't really prove anything about the system. You might say, well, once I have this model, this proves that in the system, there must be exactly 3 fees, exactly 3 points. And that's not necessarily true. It's possible that maybe you could come up with another model that has a, what do we prove? We prove there are exactly 3 foes. Prove there are exactly 3 lines. And in this model, you'll say, yes, there's exactly 3 lines. But maybe it's possible to come up with another model, say, throw another line, that has a 4th line. It's not, because we've already proved that there must be exactly 3 lines, 3 foes, but the existence of this model doesn't prove it for us. Let's do another one, because this is an example of something called an abstract model. I want to do a concrete one. All right, so how about this? For example, fees are going to be people. Foes are going to be committees. Is that right? 2 M's, 2 T's? I think so. And belongs to, we're going to interpret this as belonging to here. And a person is a member of a committee. So literally belongs to. And the picture now looks actually very similar to the one I've just drawn. Let's come up with 3 people. So I don't know. Here's my 3 people: Tom, Bill, and Susan. Not the most diverse group of people ever, but Tom, Bill, and Susan. And okay. There are exactly 3 distinct people. Good, that's verified. Any 2 distinct people belong to exactly 1 committee. So any 2 distinct people, these 2 people, Tom and Bill, I've got to put them in a committee. Let's say they're in the, they're part of the housing committee. Okay, any other 2 distinct people, how about Bill and Susan? They have to be members of a committee. By the way, I could have put all 3 of them in 1 committee, but that's going to violate axiom 4, I believe. So Bill and Susan, let's put them in the budget committee. And Tom and Susan, I don't know. Give me a committee name. Any ideas? Let's call it affairs. I don't know. They're in the affairs committee, whatever that is. Okay, so under this model, we've got any 2 distinct people belong to exactly 1 committee. So if we choose any 2 distinct people, they are indeed in 1 committee. So that's good. Axiom 2 is verified. 3. Not all people belong to the same committee. Sorry, it was axiom 3 that would have been violated if I put them all in the same single committee, right? So not all 3 people are in the same committee, that's absolutely true. And lastly, any 2 distinct committees contain at least 1 person that belongs to both. Any 2 distinct committees. So you choose any 2 distinct committees, for example, affairs and budget, that's got Susan. You choose housing and budget, that's got Bill. You choose housing and affairs, that's got Tom, right? So once again, all 4 axioms in this model are true. So great, this is a model. So I want to try just one more. I'll give you a minute to think about this one. Fees are going to be books. Foes are shelves. so shelves in a bookshelf, and belongs to means the book is on the shelf, so is on. So try to devise a bookshelf with books and shelves sort of arranged so that all four axioms are true. So spend a minute, try to come up with a model using this interpretation. So I'm going to go with a very simple model here. I've got two shelves, just two shelves. I want exactly 3 books. So 3 books, I'm going to distribute them between the 2 shelves. And axiom 2 tells me if I choose any 2 distinct books, they have to belong to exactly one shelf. So they have to be on exactly one shelf. And I think, right, if I put 1 book here and then 2 books down here, well, now that axiom is no longer true, right? If I chose, say, this book and this book, well, they don't belong to the same shelf anymore. Right, so I think the only way I can make axiom 1 and 2 true is if I put all books on the same shelf. So now 1 and 2 are true. 1 is true, 2 is true. Not all books belong to the same shelf. Oh, damn. Okay. Well, if we already agreed that this was the only way we could make 2 be true, then 3 can't be true. And so under this interpretation, we just cannot come up with an interpretation. If we interpret fees as books and foes as shelves and using this physical interpretation of location of books, we simply cannot do this. So the axioms cannot be made to be true. How about I just say the axioms in this particular model, the way I've set them up, the axioms are not true. So it's not a model. Moreover, I simply cannot make them true no matter how I try to arrange this. But in this particular case, this is not a model because the axioms aren't true. And so I just didn't want to leave you thinking that you can sort of give your undefined terms any interpretation that you want and always build a model. Sometimes different physical interpretations just don't work. Any questions? Okay. So building models is something we'll do a lot of in this class, especially in the beginning of this class. But before we do a lot of that, I want to talk about the properties of axiomatic systems. There's 3 of them that are really big. Properties of axiomatic systems. All 3 are really big, really important concepts, but only the first one is one that you absolutely must have. So the first property is consistency. And this is a must-have. If your axiomatic system is not consistent, it's not even worth anything. Just throw it in the trash. It's really, as far as mathematicians are concerned, in logic, it's just not worth anything at all. So a set of axioms is consistent if it is impossible to deduce theorems from the original set of axioms that contradict the original axioms. So this would be really bad, right? The idea is we start off with some primitive ideas, some fundamental truths that we accept, and we prove things from them. We ask, based on these fundamental truths, what else can we show must be true? Well, it would be really bad if you could then take your fundamental truths and prove that your fundamental truths aren't true at all. Right? That would be logically really, really, really bad. You'd start proving things. In fact, if you could start proving false things, then you can prove just about anything. So the idea here is that you cannot sort of start from true results and then prove false things. Right? Everything you prove must be true after the fact. So you must have this. If you don't have this, it's not worthy of study. It's not an axiomatic system that you care about. So before we talk about the other properties, how do we show that an axiomatic system is consistent? And the answer is through models. So models are very useful here. And we actually have two types of models that we'll talk about. Two types. One is a concrete model. Lots of colons and underlines and whatever. But a concrete model is a model based on interpretations from the real world, right? So our books and shelves didn't quite work, but that's an example of a concrete model if we could have set it up in such a way it was true. But also, I suppose, the people on the committees, that's sort of a real world example. So a concrete model, so interpretation of undefined terms are taken from the real world So, for example, the committees. But you can also have abstract models as well, based on abstract ideas like the lines and points that we had. So we also have abstract models. And here the interpretations are taken from some other abstract system. And just about everything you can think of, most of what we work with in mathematics is abstract, right? Numbers, for example, maybe my fees were 3 different numbers, 1, 2, and 3. Those are all abstract concepts, but for example, we had lines and points. So the question is, how do we establish consistency. Or maybe establish isn't the right word. How do we show that it's consistent? And the answer is you build a model. So here's my question, and the answer is just build a model. The real gold standard is if you can produce a concrete model. So if we can produce a concrete model, of a system, then it must be consistent. And think about this for a second. Again, think about what consistency means. Consistency means starting from your axioms, you can only prove true statements, right? You can only prove true things, basically. Things that don't contradict your original fundamental truths. So if I had a real-world model of an axiomatic system, and it wasn't consistent, then I'd be able to take fundamental truths about the universe and prove things about the universe that aren't true, right? I'd be able to start off with a committee of people and then maybe eventually prove that there's actually, instead of having 3 people that I started with, maybe I eventually prove there's only 2.5 people, something that just doesn't make any sense, right? So this is called absolute consistency. So that's all you have to do. If you want to prove that your axioms are consistent, your axiomatic system is consistent, that logic will work in your system, that you're starting with truths and you can only prove true things, if you want to demonstrate that it's consistent, you could just build a real-world model of the axioms, make sure they're all true, and then you're good to go. The problem is we can almost never do this, right? So the problem is that we can very rarely do this. For example, a lot of times you'll be working with axiomatic systems, and maybe there's, instead of having 3 distinct fees, a lot of times in your systems you'll have infinitely many fees. Well, how can I ever model infinitely many things in the real world? There just aren't ever infinitely many things in the real world, right? Infinity is an abstract concept. So if I have infinitely many objects, I can't model that with a real world example. For example, we may need to model infinitely many fees. Something that just has to be done abstractly. So that's okay. We're still going to build models if we can, and we're just going to be building abstract models. The problem is we don't establish what's called absolute consistency anymore. We establish relative consistency. I know there's a lot of writing in this stuff. I'm just trying to get all this terminology sort of out of the way and written down. So when using abstract models, we use concepts from other abstract systems. Axiomatic systems. For example, real numbers. In the case of geometry, lines and points. Etc. And as long as I'm willing to accept that my other abstract system I'm borrowing from is consistent, for example, if you believe that arithmetic or real numbers, whatever, is based on actual logic that's sound and consistent as an axiomatic system, or if you believe that lines and points from geometry, if you believe that geometry is a consistent axiomatic system, then as long as that stuff is consistent, as long as all that is logically sound and makes sense, then since we have a model based on it, then our model must also be consistent. And this is called relative consistency. So if we are willing to accept the consistency of the abstract system we are borrowing from, then we have established the so-called relative consistency. Of our system. In other words, I'm allowed to build a model using these abstract concepts, and that model can establish consistency of my axiomatic system as long as I believe that lines and points are consistent, right? So one model is consistent as long as the other one is, and vice versa. And because no one really disputes whether real numbers are logically sound, whether the axiomatic system behind real numbers is consistent, then it's totally fine to use these abstract concepts as your starting point. Okay, so there's consistency. We'll talk more about that sort of maybe next time. But two, we've only got, what do we end? 55? We got 15 minutes. Independence. Independence. I'm not spelling it correctly. Independence. Consistency was something we had to have. Independence is optional. Optional, but it's good. And in a nutshell, I'm really talking about independence of axioms. So not necessarily the whole system, but independence of the axioms means that none of your axioms are redundant. And these are terms you've probably heard before in linear algebra. I don't necessarily mean them in the same way. What I mean by that is, for example, I can't take the first 3 axioms and prove as a logical result number 4. All right, so they all have to sort of stand alone as fundamental truths that aren't results of the other axioms. So an axiom is independent if it cannot be logically deduced from the other axioms. And the entire set of axioms, is independent if they all are. Is independent if they all are. So why do I say this is optional? Well, is it really a big deal? For example, we proved, right? We proved that in this axiomatic system, we proved there's exactly 3 foes, right? So is it really a big deal if I come in and I say, as an axiom now, there are exactly 3 foes? Does it change anything? Doesn't change anything about the consistency of the system. Everything that I could prove, I can still prove. So if I just throw in an extra axiom here that isn't independent, that can be proven from the others, it's not a big deal, but it is aesthetically unpleasing. It's redundant. Why have an axiom that you don't need? And there are reasons to do this. For example, sometimes teaching things. For example, the axioms that underlie all of geometry. There's something like 22 or 23 of them. I don't believe they're all independent, and well, depending on which axiomatic system you go with. But some of the reasons behind that are for example, it's easier to teach. Sometimes just getting rid of a redundant axiom makes things a whole lot harder from your starting point. So there are reasons to go with redundant axioms that aren't independent, but you don't usually want to. If you do, it's not a big deal though. And going back to Euclid's Elements, of course he has 5 axioms, 5 postulates in it. And the 5th postulate, people debated for hundreds of years, actually thousands of years, whether the 5th postulate was independent or not, whether you needed it. Turns out you do, because if you get rid of it, then you end up with non-Euclidean geometries, hyperbolic geometry, for example, which is where we're going. But, let's see. How do you establish independence? Turns out it's fairly easy. Use models again. We can use models to establish independence. So here's the logic here. We're going to have to think this through, but here's the logic. Suppose we can produce a model, and I'll put this in quotations because it won't be an actual model, but suppose we can produce a model where one axiom is false or incorrect, and let me put an extra word in here, and all of the others are true or correct. then the incorrect axiom must be independent. I want you to think about the logic here. Suppose I came into our fees and foes again. Suppose I built a model where axioms 2, 3, and 4 are true. Okay? So I built a model where axioms 2, 3, and 4 are true. So I'm building a model for this brand new axiomatic system where I don't have axiom 1. I just have axioms 2, 3, and 4. I built a model where 2, 3, and 4 are true, so it's a consistent model, or it's a consistent system. And from 2, 3, and 4, I can only prove true results, right? But in my model, 1 is not a true result, right? I've built a model, say, here's a model using 2, 3, and 4. 2 vertices, so 2 fees. Any 2 distinct fees have a line between them. There we go, that's true. 3, not all, this is not a, using 2, 3, and 4, this is not a true, this is not an accurate model, right? Can I fix this? Well, instead of having just a graph like this, I could build what's called a multigraph. I could have 2 lines between the same 2 vertices. Okay, so 2 is still true, right? Any 2 distinct points, crap. Any 2 distinct points belong to exactly one foe. Yeah, I was trying to go to, what if we go 4? All right, let's go 4 points. Any 2 distinct fees belong to exactly one foe. Any 2, 1, 2, 3, 4, 5, 6. Any 2 distinct fees belong to exactly one foe. That's true. Not all fees belong to the same foe. That's true. Any 2 distinct foes contain at least one fee that belongs to both. Damn, that's not true. The good news is we're going to fix this by backtracking everything I've done so far. So maybe not good news. 1 is true. There are exactly 3 distinct fees. Okay. Let's go with 2 is false. Okay. I'm going to build a model. This is a whole lot easier in this case because when I fix the number of vertices, I can't do a whole lot. So I want to build a model for this axiomatic system just using axioms 1, 3, and 4. 1, 3, and 4. So axiom 1, if I wanted my model to be true or incorrect, I need 3 foes, or 3 fees, 3 vertices. Not all fees belong to the same foe. So far this is vacuously true, right? So that's good. And any 2 distinct lines, I suppose this is technically a model for 1, 3, and 4. But what I had in mind was I'm actually going to throw in some lines here. If I do this, there's still exactly 3 points. 3, not all points belong to the same line. That's true. Any 2 distinct lines contain Any two distinct lines contain at least one. What have I done wrong? Any two distinct points belong to exactly. Let's just do something stupid like this. Is axiom 1 true? Yes, there's 3 points. Is axiom 3 true? Not all points belong to the same line? Absolutely. 3 is true. Is axiom 4 true? Any two distinct lines contain at least one point that belongs to both. Yes, axiom 4 is true, but axiom 2 is not. Right, any two distinct points belong to exactly one line. Well, axiom 2 is not true because these 2 points belong to the same line. However, I don't care about axiom 2 because I'm just building a model for this new axiomatic system using just 1, 3, and 4. Because I have a model, it's consistent, I can only prove true statements. Well, statement number 2 is not true, right? Therefore, it's impossible to logically deduce from 1, 3, and 4. I cannot possibly deduce from 1, 3, and 4 statement number 2. Therefore, axiom number 2 must be independent of the others. Because if it wasn't, I'd be able to prove it, but I cannot prove it because it's false in this system. So there's the logic. This is sort of because. Let me deal with the way I've written this, it's nicer. Because only true or correct statements can be deduced in consistent systems. So your homework tonight is to go home and think about this. Think about this logically. Make sure you're happy with sort of why this works. Why, if I build a model where one axiom is false but the others are true, why that must mean that that original axiom that I assumed is false, or build a model for which it's false, must be independent of the others. Think about that logic. Make sure you're happy with it. What I want to do at the beginning of next class is try and build models for the others. Number 1, we've already established this is sort of a pain, but we'll at least we'll show that 3 and 4 are independent as well. And we'll pick up there next time. So.